Right. So I will basically continue the talk of Russ because I will be talking pretty much about the same things. The only difference is that the heuristic which we will be using will be distributed. So as Russ was talking about distributed search, they were using only the heuristic computed by one agent, and we try to also distribute the computation of the heuristic and still preserve the privacy. Okay, so I can skip the definition of mutation strips, I guess. So we have this problem which is like distributed among the agents. So each agent has just some of the actions. And the facts which are shared by the agents are public. And the actions which use the facts, the public facts are public as well. So again, we use the same search algorithm. So each agent searches its own search space and sends states which are expanded using a public action. And as I said, the original multi-agent distributed A* used a heuristic computed on projected problem. So what is a projected problem? It is the problem, as we have seen, but the agents share their public action. So each agent, for example, this action A3 is provided by this projected version, which is restricted just to the public facts. So no private information is disclosed, but the agent has some information about the public actions of other agents. So what is nice about the projected approach is that we can quite easily reuse the existing heuristics. We just feed in the projected problem, it computes heuristic, and we can use it. It's easy to compute, there is no communication, and it maintains completeness of the heuristic and admissibility, so that's nice. But if we look on some problem like this, where we have two agents, each of them have a sequence of private actions followed by a public one. Here we can see that the optimal cost is quite obviously n+1. What happens in the projection is that the agent thinks, like the first one, for example, thinks that the other agent has just this public action, and because it has no preconditions, it's applicable in the initial state. So he thinks that the cost of this problem, like the optimal cost of this problem, is 1. Obviously, any admissible heuristic cannot overestimate this estimate, so it can never be higher. We can enlarge this problem in any sense. We can extend it to any number of agents. And although this one was kind of like artificial problem, like much similar subproblems appear in the benchmark domains and in practical problems. So how to solve this problem? As I already said, we will take some existing admissible heuristic and we will distribute it in a way which maintains the admissibility. Moreover, we will distribute it in a way which gives provably the same estimates for the states as would give the global heuristic, like a centralized heuristic on the global problem. So we have chosen the LMCAT heuristic as the admissible heuristic, which is heuristic by Malte-Helmet and Karmel-Domschlag. And the basic idea is that we compute a sequence of disjunctive action landmarks, and we use their cost as a kind of cost partitioning. So what is a disjunctive action landmark? It is a set of actions such that in each plan which solves the problem, some of the action in this landmark has to be as part of the plan. So here we apply it on a relaxed problem, so it's a relaxation heuristic. And the cost of the landmark is the minimal cost of the actions which are in the landmark. And from now, if I say landmark, I mean this kind of disjunctive action landmark. Okay, so I will demonstrate how the centralized LMCAT heuristic works on the kind of centralized version of the problem. So we have no agents here. We have 5 actions. They have preconditions, add effects. It's a relaxed problem, and costs. So in the first step, we compute Hmax heuristic for all the facts. And the Hmax heuristic is then used to select one precondition for each action, is some kind of precondition choice function, which chooses the precondition which maximizes the Hmax. And based on this precondition choice function, we can construct something we call justification graph, where the facts are nodes, and the edges represent that there is some action which has precondition on this fact and effect on this fact, and the action is in the label of the edge. And there might be like one action might be in multiple labels, and multiple actions can be in one label. So the basic principle is that we are looking for cuts in this graph. So first of all, we search for all facts which are from which the goal is reachable by a zero-cost path. In this example, it's just the G. In the next step, we search for all facts which are reachable from the initial fact without visiting any of the red facts, like already marked ones. So in this case, it's all the other facts. And now the cut is formed by the actions which go from the green facts to the red facts. And the landmark consists of all actions which are in the labels of the actions in the cut. So here it's A2 and A5. In the next step, we determine the cost of the landmark, which is again the minimum of the cost of actions. Here it's 1 in the example. And then we update the cost function so that for all actions which are not in the landmark, we keep the original one. And for all actions which are in the landmark, we deduce the cost of the landmark from their cost. So now the cost of action A2 and A5 will be 0. So this is how the cost partitioning is done. And then we continue from the step 1, compute the H-max heuristic, and continue the whole cycle until the H-max of the goal is 0. And in that case, we return the sum of the cost of the landmarks found so far, and this is the heuristic estimate. Right, so now we want to distribute this heuristic. So the main idea and principle will be that one of the agents will be called initiator agent, and he will work on the projected problem. So he will work on his own actions and on projections of other agents' public actions. And the other agent will, we call participant agents, will work on kind of complement of this, which we call local problem, which is even more restricted. The local problem, so this is the projected problem, and the local problem consists only of actions of the agent, but the public actions are actually stripped of the public facts. So here we can see that there are only the private facts in the problem. So this is the same for the running example. It's pretty much the same. There is just some like technical detail that we will use, keep the initial and the goal facts there, but there's just technicality. Okay, so now we need to compute the H-max heuristic. We do it in a distributed way. Unfortunately, I don't have time to describe it here. But what is important is that the resulting H-max values are exactly the same as would be for the centralized H-max on the global problem. So we use this to construct a distributed justification graph, which again, it consists of a kind of projected justification graph, which is this part, and the local justification graph, which is this part. So what may happen here is that the precondition or effect of some action is missing because the maximizing fact is either private to different agent or it's public in this case. But it's okay. It's just like this kind of distributed graph structure. And now and there is one detail that the tie-breaking mechanism is modified that it always prefers public fact. Okay, now what we need to do is to perform the similar steps as was in the centralized version of the heuristic. So first we find all the facts which are from which the goal is reachable by a zero-cost action. This is like the second iteration of the algorithm, so costs of A1, A2, and A5 are already 0. So in this case, the facts we are looking for are P4 and like this special fact. What is important here is that we have reached this projected action during the search. So in that case, the initiator agent sends a request to the owner of the action, and the owner of the action continues the search from this action. Now he can find only this fact from which it is reachable through a zero-cost path, and it sends in reply all public actions which were encountered on the way. Here there are none. So like the basic principle is that we will continue the search from the projected action respective to the public actions which are returned by this reply. So we can kind of search through all the distributed graphs. The other way is similar, so I will just go through. So that finally all the same facts which would be marked by the centralized version are marked by the distributed version as well. And now we can extract the landmarks. One thing we have to do is that the participants, when they extract their landmark, they send it to the initiator agent. But as we want to preserve the privacy, we are not sending the private actions. But instead of all private actions, we put some kind of placeholder action, which cost is the minimum of the cost of the private actions. So we need to maintain the minimal cost, but we don't want to share all the actions that were encountered. So the initiator agent puts all the received actions in the landmark. The other agents keep their own landmarks. Now the initiator agent computes the cost of landmark using the same formula. He updates the cost function, and what he needs to do is to send the cost of the landmark to the participant agents, and so they can update their private actions, and to send the cost of the projected actions to their owners, so they can update the cost of their public actions because they might not be in the landmark. So now again we have the same cost update as would be in the centralized version. Okay, so that was the principle. Now some results. So those are results for the ratios for the heuristic for initial state. So we have seen it in the Rust talks that for some problems the distributed heuristic gives significantly higher heuristic estimates. For some problems it's pretty much the same. So some more details. Concerning coverage, this is those two columns. We can see that the distributed heuristic has higher coverage than the predicted one on this set of benchmarks. It of course depends on the benchmarks, and it also depends a lot on the communication. Here we use just a local loop through TCP/IP, so it's quite a fast communication. So what is interesting here, the next columns, this is the ratio of the initial state heuristics, average for each domain. This is the same for expanded states, for total time per problem, and total time or evaluation time per state. So what is, for example, interesting is this logistics domain, where we have much higher coverage, and it is because the heuristic, the distributed one, is much more informative. So the projected one has to expand much more states. And also it's interesting that although the distributed heuristic has 100 more times time per state, the overall time is better for the distributed one because of the number of expanded states of the projected one. So here we can see that when the heuristic is there's a difference in the heuristics, the distributed one has better coverage. From some number of similarity of the two heuristic estimates, the projected one gets better, except for the woodworking domain, where again we can see that the time difference per state is not that big, and the heuristic, although the values are much similar, the informativeness is different because there's some one private action which makes things quite different. So here again we can see that the overall time of the distributed heuristic is better. On the other domains, the distributed heuristic takes a longer time, but it's not that dramatic difference. We are actually expected to be quite worse. Okay, so the conclusion is that if we use the privacy-preserving mutation distributed A star, we can get some improvement from computing the heuristic in a distributed way as well. We have some future work. Currently, we are working on using the idea of iterative LM cut to decrease the number of necessary distributed computation. So just to improve the performance. Okay, so that's all from